Thank you so much for watching this video, and thank you to the organizers for inviting me. So today I'm going to talk about parabolic subgroups of infinite type Artin groups. So let's get started. So first, a little bit of background about Artin groups and the notation that we'll be using. So to define an Artin group, we're going to start with a graph. It's going to be a simple graph, so no loops or multi-edges. The set S is representing the vertices in the graph. And each edge in the graph has a label with an integer that's greater than or equal to 2. And then from this graph, we get this group presentation that's outlined right here. So the vertices represent the generators in the group, and each relation comes from an edge in the graph, and it has this alternating pattern. So if there's a edge labeled 3, for example, then I would get Si, Sj, Si is equal to Sj, Si, Sj. So let's just look at a brief example of this to see what it looks like. So here's my defining graph. I have 3 generators because I have 3 vertices. Here's my 3 generators right here, A, B, and C. And the edge labeled 2 is giving me a commuting relation between A and B. And the edge labeled 3 is giving me this relation that's called a braid relation, this BCB equals CBC relation. And there's no edge between A and C here, so there's no relation between A and C. So some other examples of Artin groups include free groups. So if there's no edges in the graph, then you get a free group. You can also have a free abelian group if all of the edges are labeled 2. If all the edges are labeled 2, or if there's possibly edges missing, these groups are called right-angled Artin groups, and they're a very well-studied subclass of Artin groups. So sometimes when you hear people talk about Artin groups, what they really are talking about is right-angled Artin groups, but in this talk we're talking more generally. And another example of Artin groups are braid groups. And finally, if you take 2 Artin groups and you take their free product or the direct product, then you get another Artin group. So this is really a very broad class of groups. And I should say, I think there may be other people in the conference talking about Artin groups, and sometimes people use a slightly different notation with different edge labels for the graphs. So just be careful when you're looking at other talks. They may be using a slightly different notation, but this is the notation that we're going to use in our talk. So Artin groups are very closely related to this other kind of group called Coxeter groups. And Coxeter groups are defined in the same way. So you start with a graph, and you get all of the same generators and relations as with the Artin group. But I'm adding this other relation right here, which is that all of the generators have order 2. And in many ways, Coxeter groups are more well-studied than Artin groups. They're sort of the more familiar version. So Coxeter groups are really inspired by groups of reflections. You have that generators all being order 2, so those you can think about those like reflections. And some examples of Coxeter groups include symmetric groups, dihedral groups, Weil groups for certainly algebras. You can think in terms of the symmetric group acting on the complex space by permuting the axes. So that is an action by reflections. So that's really what's happening there. And the symmetric group is the corresponding Coxeter group that corresponds to braid groups. So the relationship between Artin groups and Coxeter groups, you can think of it as sort of a generalization from the relationship between braid groups and symmetric groups. So today we're going to be talking about a particular kind of Artin group. So Artin groups whose corresponding Coxeter group is finite, that has finite number of elements, are called finite type. So all Artin groups always have an infinite number of elements, but sometimes they correspond to Coxeter groups that have a finite number of elements, and these are called finite type. And in the same way, if the Coxeter group has an infinite number of elements, then the Artin group is called infinite type. And here is my little Venn diagram of different types of Artin groups that you might be interested in. So here's the finite type that I just mentioned in this little circle right here. So this is when the corresponding Coxeter group is finite. You also, I already mentioned right-angled Artingroups right here. So these are when all the edges that are there in the graph are labeled 2, or there might be some edges that are missing. Sometimes we say that those edges are labeled infinity. And so these small circles represent 2 different well-studied types of Artingroups. And then this large circle represents a more general type of Artingroup called FC type. FC type Artingroups were defined by Charney and Davis in 1995. And they are Artingroups where every clique in the graph, so every complete subgraph, defines a finite type group. And these FC type are important because there's a particular cube complex that you can define for Artingroups, and it's going to be cat 0 when the Artingroup is FC type. So that's sort of why they're important for us. And there are other Artingroups out here that are not FC type, that are just even more general. And in general, many questions about Artingroups have been answered for right-angled Artingroups and have been answered for a finite type, and maybe are partially answered for FC type, but most questions are open. Sort of in general, this area out here where the most general Artingroups are living is very mysterious, and there are a lot of open questions out there. But today I'm going to talk to you about some results of mine that are known for finite type, and where I'll be generalizing to this middle circle here, to this FC type case. So I'm talking today about parabolic subgroups of Artingroups. So let's talk about what those are. So a parabolic subgroup is a special kind of subgroup, and it's always given in this form. So I take a subset of my generating set, and I look at the group generated by that subset, and then I'm allowed to conjugate that group by any element in my group. And whenever I do this, I get something called a parabolic subgroup. And parabolic subgroups are important chiefly because of this theorem of van der Lijk. This is part of his PhD thesis, which says that if I have this graph gamma and I look at the subgraph that's spanned by the vertices in my subgroup T, and I define my Artingroup just using that subgraph, then I will get the same group as my parabolic subgroup. So this really shows that the parabolic subgroups are like little Artingroups inside my big Artingroup. They're sort of the building blocks for my larger Artingroup, and understanding how they interact with each other, understanding how they sit inside this larger Artingroup is going to give us lots of information. So here's some different avenues of investigation different questions that you could ask about parabolic subgroups. And these are things that are partially answered in some special cases. If you think back to that Venn diagram at the beginning, these are things that are known for the smaller circles, and I'm going to be talking about some generalizations to that larger FC type circle, and are still open in most general sense. So one avenue for investigation is something you could ask about any subgroup, right? What is the centralizer of the subgroup? What is the normalizer? Is it a normal subgroup? That kind of thing. This is very much something that there's some progress on, but is an open question in general. And then here's a question that I think is surprising that we don't know it already, is that given two parabolic subgroups, when is their intersection a parabolic subgroup? So in terms of thinking about Artingroups as sort of little, these parabolic subgroups as little Artingroups inside my big Artingroup, I might want to ask, well, how do they interact with each other? Do they form a lattice, for example? Do they just, what is their intersection? So this is really the first step towards trying to get a handle on that sort of structure. And this is a result that is shown in the finite type case, and that I will be generalizing to the FC type case in this talk. So I just wanted to talk briefly about ribbon elements. Ribbon elements are one of the main reasons why these are a challenging question. And the term ribbon is given by Gödel in 2003. And basically, the idea is that there are these elements. This element is called R in this example, where when you conjugate by R, you permute the elements of the generating set. So in this example, I have my defining graph is a very large n-gon. I've just got this big long loop in the graph, and all of the edges are labeled 3. They could really be any odd number. And there are elements where when I conjugate by that element, I permute the vertices on the edge. So there's an element where when I conjugate by that, I conjugate S by that element, and I get this generator. And then I can conjugate by another element and get this generator, and so on, and I can conjugate all the way around and get T. And even more than that, I can conjugate, and I can conjugate, and I can keep conjugating by this element, and I get this word that's a very long word. It's a word that includes all of the generators in the whole group. It includes T, which, S and T have a free relation between them, so you would think there would be very few relations between them. But when I conjugate by this word, I actually get back to S. It's in the centralizer of S. So these groups have very large centralizers, and in general, that's one of the reasons why this is a difficult area to study. This is not true in right-angled Artin groups. This is one of the reasons that Artin groups which are not right-angled are more difficult to study. So here's some results. These are results that are originally in the finite type case, proven by Completo, Gebhardt, Gonzalez, Meneses, and Wiest, and then generalized to the FC type case by myself. So suppose I have an Artin group, and P and Q are two finite type parabolic subgroups. Then their intersection is also a finite type parabolic subgroup. And as I said, it's just sort of surprising how difficult it is to, Completo et al.'s original paper for this is many, many pages long just for this seemingly very simple lemma. So it's an interesting result, and I'm going to tell you a little bit about the proof of it in a few minutes. But first, I wanted to tell you one more avenue for investigation in this area, just to describe it to you. So this avenue is to try and create a curve complex, an analog to the curve complex for Artin groups using parabolic subgroups. And this is something that I know that Maria is speaking about in this same conference, so I'm going to talk about it very briefly, and then if there are other questions about it in the question and answer session, I'm happy to answer them. But the idea is that if we think about the braid group case, right, so braid groups are both mapping class groups and Artin groups. So we already know what the curve complex looks like for braid groups because they are mapping class groups. And we want to know, to build on this, to try and get a complex that will behave like the curve complex for Artin groups. And the idea is to use this bijection. So there's a bijection between the curves in the punctured disk. So the braid group is the mapping class group for the punctured disk. So the curve complex is made up, the vertices are curved. These are the vertices in that curve complex. And there's a bijection between those and the parabolic subgroups in the braid group. And it works like this. Here's just some examples. So here's a curve, and it corresponds to the subgroup generated by the element that permutes these two punctures and the element that permutes these two punctures. And similarly, if you have more complicated curves, then you can get parabolic subgroups that are conjugates like this. And so the idea is to use this bijection and define a new complex for all Artin groups, and to try and find a complex that has similar properties to the curve complex. The idea is really that in the same way that I have the curve complex is measuring some properties of subsurfaces that sit inside my surface. So the new complex that we want it to somehow measure these parabolic subgroups, these little Artin groups that are sitting inside my little Artin group, and figure out how they're interacting with each other. So this is the definition of this new candidate complex that we're working with. This is very much an open avenue of research at the moment. So this was defined in that same paper by Completo, Gebhardt, Gonzalez-Meneses, and Wiest. And they define this using this definition that I have here, and then they show that this definition is equivalent to several other definitions. And then I sort of extend the results to Artingroups of FC type. And just very briefly, so the vertices in this complex are parabolic subgroups. Proper means they're not the trivial group, they're not the whole group. Finite type, we've already talked about. That means the corresponding Coxeter group is finite. So the entire group can be FC type, but the subgroups need to be finite type. And then irreducible means that they don't decompose as direct products. And then one of several equivalent ways to define the edges in this complex is to say that there's an edge between two subgroups if the centers of these subgroups commute. So these being finite type irreducible parabolic subgroups, one of the things that we know about these subgroups is that they have center infinite cyclic, so they have center isomorphic to Z. So each of those centers has a generator, and you just look at whether the generators commute. But the technical pieces of this definition are not so important for what we want to talk about today. Really, I just want to point out some of the properties that we know of this complex. So one complex we know, or one property that we know of this complex, is that in the braid group case, it is the curve complex on the nose. It's the exact same complex when we look at it in terms of that bijection that I had on the slide earlier. So this is really showing us that this is a good idea. And the other thing is that it agrees with something called the extension graph, which is a graph that is defined by Kim and Coberta for right-angled Artingroups. And this is one of the examples of the spaces that are really considered to be a good analog for the curve complex in the right-angled Artingroup case. So the fact that it agrees is a good sign for us in terms of we're trying to define this analog. And it also has some of the same properties that the curve complex has. So, for example, in both the curve complex for the mapping class group and in the complex of parabolic subgroups for Artingroups, we know that every n simplex in the complex represents a Zn subgroup inside the group. You can see that really from the definition that I just gave you. We also have know that it is, except for a few exceptions, we know that it's connected and that it's infinite diameter. So that's another nice result that mirrors what's happening in the curve complex case. But one thing that we don't know, or we only know in very limited examples, is this new complex delta hyperbolic. So this is really the most current avenue of study for this area, is to take this complex and try and figure out is it delta hyperbolic or not, because this would be one of the main properties of the curve complex that we want to mirror. So that's all I have to say about the complex of parabolic subgroups. Again, I know that was a very brief introduction, but hopefully if there are questions about that, I can answer them in the question and answer session. And now I want to talk to you briefly about the proof of the theorem that I promised you. I promised you a proof of the theorem that the intersection of two parabolic subgroups is a parabolic subgroup. And I'm highlighting this proof because I think it's an interesting proof, and it sort of gives a good example of the ways in which we often use these geometric tools to extend results about finite type Artingroups to results about infinite type Artingroups. So the main geometric tool that we use when we want to make an argument about an FC type Artingroup is this cube complex. It's called the Deline complex. And I'm just giving you sort of a brief summary of its properties. So first, it's a cat zero cube complex. You can define this complex for any Artin group, but it's going to be cat 0 with the usual cubical metric only when the Artin group is FC type. So that's the reason for this restriction on the types of Artin groups that we're looking at. The vertices in the cube complex are cosets of these particular subgroups. So these are like a special kind of parabolic subgroup. They're parabolic subgroups that haven't been conjugated by anything. And we are insisting that they're finite type. And then I'm allowed to take any coset that I like. And then for any pair of vertices, the adjacency relation for this cube complex is just determined by the inclusion of these cosets. These are sets in the group, and I can see whether they're included into each other or not. So the main thing that I want you to know about this complex is that the stabilizer of a given vertex, so the Artin group acts on the complex by isometries, and the stabilizer of a given vertex is the parabolic subgroup. So we can study parabolic subgroups by looking at this action and looking at the stabilizers of the vertices. So this is just a brief example to show you a subcomplex of the Deline complex to give you a sort of a picture of how it works. So this is my defining graph gamma here. And this is the fundamental domain. So this is the all of the subgroups here before I've taken any cosets or anything. These are just the identity versions of the coset. A empty set is the trivial group. We include the trivial group here. And the edges and the cubes are defined just by inclusion. So the trivial group is included in all of them. The group generated by S is included in the group generated by R and S, etc. And then you multiply by the cosets, and you get sort of like this little cube and edge flag picture. You're going to get it translated all around. So here's an S translate, here's an R translate, here's a T translate. You'll get the TS translate over here, and it will extend in all directions it's definitely an infinite diameter complex. So that's sort of how the Deline complex works. And just to remind you, this is the goal of this proof that I'm trying to explain to you. So remember, we're trying to show we're given an FC type Artin group. So we're given a group that has a cat 0 Deline complex. And I'm given two parabolic subgroups. So those are going to be stabilizers of particular vertices in my complex. And I want to show that the intersection of these parabolic subgroups is also a parabolic subgroup. So how do I do this proof? First, I'm going to choose VP and VQ to be vertices that are fixed by P and Q, so that the stabilizer of P is equal to, the stabilizer of VP is equal to P, and the stabilizer of VQ is equal to Q. So here's my picture. I have VP and VQ. And because this complex is cat 0, there's a unique geodesic between these two vertices. And this geodesic is fixed pointwise by the intersection of the parabolic subgroups. And so more than that, we have the straight geodesic that can go through the interior of the cubes, but sort of surrounding that, we have this edge path. And because of certain properties that have to do with how the Artin group acts on the Deline complex, if this geodesic is fixed by P intersect Q, then this edge path will also be fixed by P intersect Q. So now we have this edge path, and each of these vertices has a stabilizer, and each of P intersect Q also stabilizes each of these vertices. So we're starting to see some relations between P intersect Q and the stabilizers of these vertices. In particular, so remember that the edges in the Deline complex are determined by inclusion. So you can put a direction on each of these edges. I've drawn it in this, up, down way to suggest that. So this determines a sequence of what I call turning points in this edge path. And we get some relations between the turning points. So in this example, for example, the stabilizer of V1 is contained in the stabilizer of VP, because I have sort of a downward edge going here. And then I have the stabilizer of V1 is also contained in the stabilizer of V2 because I have these downward edges like this. So you get all of these relations between the stabilizers of the turning points, and this will help us in our goal. So we're going to proceed by induction on the number of turning points. So R is going to be the stabilizer of the very last turning point. And I'm going to use my induction hypothesis. Remember, I'm trying to show that the intersection between P and Q is a finite type parabolic subgroup. So I'm going to assume that the intersection between P and R is a finite type parabolic subgroup, just because I have one fewer turning point in the sequence between P and R. So that satisfies my induction hypothesis. And then the final step of this proof is just split into two cases. So I have the case where R is contained in Q. So this is the case where that up, down path ends in an upward path, like in the example on the previous slide. And in this case, you see that P intersect Q, which is the group that we're interested in finding out about. It fixes the entire edge path. So in particular, it fixes the second to last turning point. It fixes Vn-1, so it's contained in R. And if you take these relations together, the fact that R is a subset of Q and the fact that P intersect Q is a subset of R, you get that these two groups are equal. And so then we know that P intersect Q is a finite type parabolic subgroup because that's what we assumed to begin with. And then the second case is the case where Q is a subset of R. And so this is corresponding to that up, down path. The very last piece of the path is going to go down. And in this case, we really just get to reduce to the finite type case, which was already shown by Completo et al. Previously. So this is, I hope that's the end of this proof. I hope you learned something from it. I think it's a very interesting, simple argument that shows, it's a good example of the kinds of arguments that you can make using this Deline complex and how to argue to extend an argument about a finite type group to a FC type group. That's the end of my presentation. Thank you so much for listening. Please come to the live question and answer session on June 2nd. And either you can submit your questions to the conference or just come and show up with your questions and I will be happy to answer them. Thank you so much for listening.